All right, welcome back, everybody. Today, we're going to go ahead and spend a second day talking about the other kinds of operations you can do with complex numbers. A reminder that on the first day, we learned that the complex numbers existed. We learned about how to add and subtract them. We learned how to write our answers in standard form. And so today, we're mostly going to talk about solving with imaginary numbers and also multiplying with them. So when it comes to multiplying complex numbers, you're going to use the distributive property or FOIL, just like you would with real numbers. You should make sure that your final answers always combine the like terms, are written in standard form, a plus bi, and of course, every time you have an I squared, you're going to replace it with a -1. The two main facts you need to recall from yesterday are the definition of I, which is the fact that the square root of -1 is equal to I, and the fact that I squared is equal to -1. So notice here that in the first set of examples, you're being asked to multiply. So sometimes that means to distribute, sometimes that means to FOIL. You're going to go ahead and multiply. You're going to then combine and simplify any like terms that you can. And of course, you're going to have to make sure that you always give your answers in standard form, which means a plus bi, which of course is the real part first and the imaginary part second. So here in number 1, you're being asked to multiply 6 times 10i. You're going to multiply the real parts, which would be 6 times 10, which is 60. 60 what? 60i. Nothing to simplify, nothing to combine, so that's your final answer. Number 2 is an identical problem, except for the fact that there are no parentheses. So whether there are parentheses or not, it doesn't matter. You're going to multiply the real part, 3 times 5, which is 15. 15 what? 15i. Here in number 3, you're multiplying a monomial 2 times a binomial. So that, of course, means you're going to distribute. When you distribute 2 times 7, you get a 14. When you distribute a 2 times a -4i, you're going to multiply the real part and get a -8i. Because your real part is first and because your imaginary part is second, that would be your final answer. Now, don't take the problem farther than it needs to, even though there is a common factor to 8 and 14. You don't want to divide, you don't want to factor, you just want to make sure your answer is in standard form and then call it a day. Here in number 4, you're also distributing, but with a negative this time. So a -3 times a 5i, that's a -15i. A -3 times a -6, that's a +18. That is a good answer, but a better answer would be to put the real part first and to put the imaginary part second. Notice that when I do that, when I change the order, I leave the 18 positive and I leave the imaginary term negative. You're simply just inverting them. You're not actually changing their signs. So now let's take a look what happens in the next set when you're multiplying an I times an I. So in number 5, you're multiplying a 2i times a 6i. And again, look at number 5, look at number 6. Whether there's a parentheses or not, you're still just going to go ahead and multiply. So you're going to multiply the real numbers together. 2 times 6 is 12. Then I times I, you're going to add those exponents, and 1 times 1, or 1 plus 1, would give you I squared. Of course, you'll recall that I squared is always equal to -1. So this is really 12 times -1, which means your final answer is simply -12. In number 6, 5i times -9i. A +5 times a -9 is a -45. And I times an I, you add those exponents. 1 plus 1 gives you 2, so I squared. Then your I squared is always going to be replaced with a -1, making your final answer a negative times a negative, which of course changes into be a positive. Now in number 7 and 8, we're back to distributing, but now you're distributing an I, so just make sure you proceed with caution. An I times a 2i, you're going to get a 2i, add the exponents, squared, minus 7i. Anytime you see an I squared, you're going to replace it with a -1. So that's going to give you a -2 minus 7i. And again, you always want to have the real part first and the imaginary part second, which you do here. And then finally, when you go ahead and multiply that 4i distributing, you're going to get a 32i plus a 12, add the exponents, I squared. A positive 12i squared becomes a negative 12 when you replace the I squared with a negative 1. And for your final answer, make sure that you put the real part first and the imaginary part second. So after you've done simple just distributing and multiplication, we now, of course, have to do our FOILs. So a FOIL would be something like number 9 and number 10. You're going to FOIL the same way you would with real numbers, doing your first 6 times 4. Sorry, that's a positive 24. Then your outers, negative 18i, followed by your inners. 4 times 2i is 8i, followed by your last, be very careful here, a positive 2 times a negative 3, that is a negative 6. I times I gives you an I squared. A negative 6i squared, because I squared is negative 1, a negative 6 times a negative 1 becomes a positive 6. You're then going to add the real parts, so 24 plus 6 gives you a total of 30. Negative 18i plus 8i is going to give you negative 10i, and because your answer is in standard form, then you're done. When you go ahead and FOIL number 10, you'll notice, hopefully, something special about those two binomials. Notice that they have the same front, they have the same back, but they have the opposite middles. So whenever you're trying to multiply a pair of binomials that have the same front, the same back, and the opposite middle, those are called a pair of conjugates. And something nice always happens when you're multiplying a pair of conjugates. So when it comes to imaginary numbers, a conjugate would be A plus BI, followed by A minus BI. Again, they'd have the same front A, the same back BI, and then opposite middles. When you're trying to FOIL a pair of conjugates, remember you only need first and last because the outers and the inners will always cancel out. So if you multiply just the first, you're going to get A squared. If you multiply just the last, you're going to get negative B squared times I squared. Remember, of course, that anytime you see an I squared, that's really a negative 1, which means that anytime you multiply a pair of conjugates, you're always going to get A squared plus B squared, meaning that there is no longer going to be any imaginary numbers as part of your answer. So that's the beauty of multiplying a pair of conjugates. And again, a conjugate means the same real parts, the same imaginary parts, but then they have to have opposite middles. And every time you multiply a pair of conjugates, you're always going to get A squared plus B squared. The imaginary terms are always going to cancel out. So if you're able to remember and use that shortcut, you certainly should. If you want to make sure that it works, then go ahead and FOIL number 10, just like you did number 9. Starting with the first, 5 times 5 is 25, followed by the outers, which would be negative 15i. Then the inners, which would be positive 15i, and then a positive 3i times a negative 3i, that would be a negative 9i squared. An I squared is equal to a negative 1, which would make this into a positive 9. Notice that when it comes to your imaginaries, a positive 15i and a negative 15i, those are going to cancel out altogether, which means all you're going to be left with is 25 plus 9, which is going to give you an answer that is completely real of 34, no imaginary answers in sight. And again, the reason why that happened is because you are multiplying a pair of conjugates. So it's a shortcut. If you realize they're conjugates, you know that your answer will always simplify nicely. If you don't realize they're a pair of conjugates, you can do the long way and FOIL, and you should still get the same answer. Now that you've done a bunch of simplifying, we are now going to solve quadratic equations with square roots. So first, let's make sure we understand why these are quadratic, because they all have x squareds. Then let's remind ourselves why they're equations. That's because they all have equal signs. Up until now, at least in this section, we didn't have any quadratics and we didn't have any equal signs. So what's different if we do have those? Well, it turns out that we're going to have to always make sure that we simplify the radicals using imaginary numbers as needed. And most importantly, we have to remember that each of our answers should in fact have a plus or minus in it. So for all these examples, in the next set, we're going to go ahead and solve for x. So some of the answers are going to be imaginary and some of them not. From this point forward, it's not that every single answer is going to be imaginary. It's just that every single answer could potentially be imaginary. So it's important that you know the difference. So take a look here at number 1. In number 1, our goal, of course, is to solve for x. If we're trying to solve for x, the first thing we want to do is get the x squared by itself, which means we're going to add 9 to the other side. Then to get the x by itself and get rid of the squared, we're going to go ahead and take the square root of both sides. The square root of x squared is just x. When you take the square root of something, you have to put a plus or minus out front. 9 is a real number, and it's a perfect square. The square root of 9 is just 3, which means your two answers are plus or minus regular 3. Remember, there have to be two answers, plus or minus, because that's what it means to be a quadratic. Compare that to number 2. In number 2, you're going to start the same way by subtracting 9 to the right. You still want to get rid of the squared by taking the square root. You're still going to get x. You're still going to need a plus or minus. But now when you go to simplify the square root of negative 9, you're going to think of it as the square root of negative 1 times the square root of 9. The square root of 9, still 3. The square root of negative 1, remember that's the definition of the imaginary unit, which means your answer is plus or minus 3i. For number 3, so start by subtracting 18. Then divide by 3. X squared is equal to negative 6. Take the square root. When you take a square root, plus or minus. The square root of negative 6, there's a square root of a negative 1, and then you can't break 6 down into anything simpler. So the only thing you can take out is an I radical 6. Remember the rules. When you have an I with a whole number, you should put the whole number first and the I second. When you just have an I and a radical, you should put the I first and the radical second. We'll see in a minute what it would look like if you have all three. For number 4, I'm actually going to go ahead and take the x squared in this case and add it to the other side. Then I'm going to get 90 equals x squared. I'm going to go ahead and take the square root of both sides. When you take the square root, don't forget the plus or minus, always, always. There isn't going to be any imaginary in this answer because there's no negative. You can, however, simplify the square root of 90. Remember, when you're simplifying radicals, you take out the biggest perfect square possible, and then whatever it's left. So plus or minus, the square root of 9 is 3. The square root of 10 can't be simplified, which means your answers are plus or minus 3 radical 10. For each of those 4 problems, the plus or minus means there's 2 answers. Half of these problems have imaginaries and half of them don't. So again, going forward, not every answer is guaranteed to have an I, but it could. Let's take a look at the next set, which looks similar, but slightly harder on the algebra. Idea is still the same, though, at least for 5 and 6. You're going to go ahead and you're going to try to start by isolating the x squared. So in number 5, you're going to add 11 to both sides, which means that 2x squared is going to equal negative 36. Then you're going to divide both sides by 2. Then to get rid of the squared, to get rid of the squared, just give me 1 second. There we go. To get rid of the squared, you're still going to go ahead and take the square root. When you take the square root, don't forget your plus or minus. You know you're going to have a negative 1. The biggest perfect square in 18 is 9, which goes in twice. And because your answer is going to have all 3 parts, you're going to put the square root of 9 first, the square root of negative 1, which is I in the middle, and then radical 2 in the back. So when you have all 3 of those values in the same answer, again, you should always put the whole number first, the imaginary part in the middle, and then the radical part in the back. For number 6, you're going to go ahead and start by adding 2. So negative 5x squared is equal to 10. Divide both sides by negative 5. And you're going to get x squared is equal to negative 2. Take the square root. Don't forget your plus or minus. You can't simplify anything from the square root of -2 except for the fact that you can take out an I. The next four problems are slightly more complicated, and we know that they're more complicated because of the fact that inside of the squared, there is something other than an x. We are not allowed to touch anything inside of that squared until the squared is gone. So we always have to work from the outside in this case. In number 7, there's nothing on the outside, nothing to add, nothing to subtract. I can't do anything with that -3 until I get rid of the squared. How do I get rid of the squared? Well, I'm going to go ahead and take the square root. The square root of x minus 3 squared is just x minus 3. When you take a square root, don't forget your plus or minus. The square root of 25, of course, simplifies to be 5. And then again, you're not solving for x minus 3, you're solving just for x. How do you solve for x? Well, you're going to add the 3 to the other side, but you're going to put that first. You're going to leave the plus or minus in the middle, and then you're going to put the 5 in the back. Most of the time, that will be a perfectly fine answer. Please know that if you wanted to, you could do 3 plus 5, which would give you 8, and 3 minus 5, which would give you -2. Those are, of course, equivalent to the answer that is in the box. It'll be up to your teacher and up to the particular circumstance as to whether or not you should go farther. Then, of course, there are some cases where you can't go farther. So in number 8, again, you can't do anything with the +4 until you get rid of the squared, which you always do by taking the square root. When you square root the left side, x plus 4. When you square root the right side, don't forget the plus or minus. The square root of 9 is 3. The square root of a negative is I. Again, we don't care about solving for x plus 4. We only care about solving for x. So to get the x by itself, I'm going to subtract 4, which I'm going to put first. Then I'm going to put the plus or minus in the middle, and I'm going to put the 3i in the back. Now, as compared to the previous problem, I could not go any farther in this case because you would not be allowed to add real parts to imaginary parts. So that is where I would have to stop, but kind of good to know when you can go farther versus when you can't. And then our final two problems here, notice that there is stuff outside of the squared, which means that's the stuff that we have to deal with first. So in number 9, before you do anything else, you're going to subtract 5 from both sides. That's going to give you x plus 2 squared equals 45, which means you're going to now take the square root, x plus 2. Don't forget your plus or minus. Since you're trying to simplify the square root of positive 45, there aren't going to be any imaginaries. You're going to break 45, though, down into the square root of 9 times the square root of 5. The square root of 9 is 3 radical 5. And then again, because you're just trying to solve for the x, you're going to go ahead and subtract the 2 and put that first. Plus or minus in the middle, 3 radical 5 in the back. And again, as much as you think you might be able to go farther in this case, you cannot. That 3 belongs to the radical 5, which means you cannot separate them. You cannot do -2 plus 3. That is just not allowed. The hardest it would possibly get is number 10, which means you are trying to isolate the x minus 1 squared, which you're going to first do by subtracting 5. Then divide by -3. Take the square root. Never forget your plus or minus. The square root of a negative means an I. The square root of 5 can't be simplified. And in your final step, again, you need to get the x all by itself, which would mean add the 1 to the other side. Put the plus or minus in the middle, and then I radical 5 in the back. So those are the examples of all the important things that you can do with i's. And again, just make sure you go back and take a look. Notice that for examples 1 through 10, there are no x's and there are no equations compared to the second set for which there are x's and there are equations. The final problem, so notice that in number 11, instead of being equal to a number, you are equal to an f of x. So in example C, what they're asking you to do is to find the zeros. The first thing you want to realize is that finding a zero is the same as finding an x-intercept. How do you find an x-intercept? Well, that means you set y equals or f of x or g of x equal to 0, and then you solve just like all of the examples that we did above. So start by changing the f of x to a 0. I'm then going to add the x squared to the left, which makes it positive. Then I'm going to get rid of the squared by taking the square root. That's going to give me a plus or minus. There is going to be an I. 60 is a pretty large number. The biggest perfect square in 60 is 4, which goes in 15 times, which means that I'm going to get plus or minus. The square root of 4 is 2. The square root of -1 is I. And then the square root of 15 goes in the back. So when it comes to saying what are the zeros or what are the x-intercepts, it's plus or minus 2i radical 15. Well, if you think about that for a second, how do you graph imaginary things? Well, you don't. So the fact that there are imaginary x-intercepts means that you do not cross the x-axis. So let's think about why that is. This is an equation, negative x squared minus 60. If you think back to your transformations, the negative that's out front means that this quadratic is going to be upside down or reflected over the x-axis. The minus 60 means that the graph is going to be down 60. So the graph is going to look like this. It's a quadratic that faces upside down. And notice that because it faces upside down and was minus 60, it doesn't cross the x-axis, which is exactly what we were thinking would happen because of the fact that the x-intercepts were imaginary. So thanks very much, guys, for tuning in. Hopefully you have a much deeper understanding of complex numbers, and we will catch you next time.